Hello, everybody, and welcome to Handmade Hero. Today we have kind of just an assignment from our past self. We have to figure out some good way to rebuild our sampling tables. Our sampling tables for lighting we found were actually broken. They had been broken for a while, it seems, so that was an issue. But they are especially showing they're especially causing a problem now because we're trying to debug the simplification to the lighting that we did, and in so trying we discovered that like the rays we're casting are totally not distributed the way that we thought they were. So what we're trying to do at the moment is, oops, this is actually debug builds, which I didn't actually mean to do. Let me go ahead and do a release build there. So there we go. So if we run our lighting as it is currently, it actually is pretty good. We're not really we're in a very good state. The problem is there's this weird like sort of color bleed that happens. And so we think we have some problems with just like maybe the apron and stuff. Like you can see when it starts up, it actually looks quite nice. So we're pretty close. I don't think we're like super far from having it work. But you can see that we've got sort of this weird like color bleed problem. Usually those feedback problems are from like we're sampling off of the apron or something is like getting over added or weird things like that. And so we need to debug that. And as we were debugging it, we realized that like as we looked at the ray casts, the ray choices of rays, there were like all of these rays pointing straight down, right? And it turns out that our sampling table, if you go and look at it, is just not correct. Like there actually is a situation where like every so often, like you see that 0, 1, 0, 1, 0, like there we should never sample the same ray twice, right? I mean, we never want to do that. And yet here we are doing that a ton of times, right? And so we clearly have bad distribution that we're putting in here. That's not good, and we really want to be able to fix that. But while we're doing it, we also probably just want to rebuild these sampling tables to be a little bit more sensible anyway, right? Because now we know that we're actually just sampling the whole sphere every time. Like before we were doing sort of an over time sampling because we were trying to sample a lot more probes. Now we just don't have that problem because we've got a lot more horsepower since we've reduced, we're not using Z anymore, Z stacks. So there's just a lot fewer probes. We can cast a lot more rays. And we also optimized the ray casting to be very fast. So it doesn't take very much time to do the samples anyway. So we probably want to do something where we just like create a sample sphere that's pretty reasonable with respect to, just chunks where we have 16 rays or so going out of one face and 16 rays going out of another face, 16 rays going out of another face. We kind of want these, like I do think we want these to be a blue noise pattern. Blue noise sampling is always better than white noise because white noise is very is going to oversample some areas and undersample others, whereas blue noise is always like fairly distributed. The problem is, how do we generate a blue noise sample that has exactly 16 points in the region of the face, the octahedral face that we're sampling from? And that's a tougher question. I can think of sort of ways we might do it. Like, for example, if you were to make a dense blue noise pattern on a sphere, and then you just, like, scale that up over, like, you just searched for a scale factor where as you scaled it up, you would get only a certain number. Like you basically like restrict the size of the stuff on the sphere until you get ones that are, yeah, but even that's not going to be the same as for distance. It's a tough problem. Like I don't know exactly how you do it. Like I don't know how you do a blue noise pattern where you basically say, look, we're going to divide the sphere into 8 octants, and we want each octant to have 16 evenly distributed sample points that are like, sort of like equally, spaced out or whatever. I don't know how you do that. I would also ask, if it just per pixel, should we just do it per pixel? Because this is another problem. So let's think about this real quick. So if we were to look at the map dim, right? The octahedral map dim is 8 by 8. So there's 64 there's 64 like texels that we're filling. Right? And let me run speed crunch. Oops. Let me run speed crunch here. If there's 64 texels we're filling, and we are actually, for each one of those texels, yeah, so there would be 16 samples per texel. Is that correct? Because we write out a row at a time. So there's 8. Yeah, so I think that's what we would be doing. It's 16 samples per texel, right? So I think what we actually probably want to do is just generate samples in the texel, probably. And Best Chartist, we don't have any temporal variance anymore. I mean, we could add some more in, but at the moment we are just sampling a fixed set of rays. And I know there's like issues with that, but the idea is to be dense enough that we don't care, because it seemed like we will be able to do that. Possibly. So yeah, like maybe the right answer is we generate a blue noise tile for the texel, and then we just compute the directions out of the texel. So, because it's not that hard to make blue noise where we generate 16 points in a square, it is, and in fact we could even use sort of something that's not quite blue noise, like something that's like pseudo blue noise sampling pattern. That's, because we don't need it to be exactly blue noise. It could be sort of like blue noise light, like you know what I mean? So we could do something like that. I'm just trying to think of what's the most straightforward way to do it. Like, the other thing is, I guess we could just tune the parameter manually. So we can just tune the blue noise distance parameter so that we know that it's like roughly correct. Like, this gets 16 and it's like a little sparse, but it's, it's good enough or something. So yeah. So let's take a look at HH Sphere, and let's just try to rewrite it to something else. Let's also get it so that we can draw it. So like if we look inside Handmade lighting, there's this like sphere drawing thing that we have here, right? So this thing draws a sphere, and so what we could do is try to get that working in some way where we can see the light values here. And if we run that, we should see like a sampling sphere sitting there, right? And the point of this, there's not a whole lot of point of this at the moment, but what we can do is we can verify by modifying this routine, we can verify that this it comes out looking evenly distributed somehow, right? Like, we can adjust this drawing routine to draw like each patch in like a different color or something, and from there we can, like, we have this get debug color 4, right? You can see this part here. So we can do something where we basically rebuild the table, then we draw the table here where we show each patch, and we can sort of verify that it's roughly correct, right? So I think that's mostly what we want. So in HH Sphere, what we would, like, I think there's, like, a fair bit of cruft in here now. So, like, things like interleave directions, like, we don't actually want this anymore. I don't think, like, we don't want some of these things anymore. Like, interleave directions, we don't want to actually do. We want to generate things differently than that. I also don't know, like, why do we even want those at the moment? That's kind of a good question. Light sampling sphere float table. Do we use that? What is that used for? There's a light sampling. So the sampling spheres are here. And the directions, like, why are there two, like, we haven't done this in long enough that I don't remember why it's doing it this way. I also have, like, no idea why there are array bundles per sphere this way. Is that because we load them as 4x values? Like, what do we do there? When we load this in, do we do some kind of... So we use something called ray d-single, which is a sample ray direction pulled out of the light sample directions, right? So it's just that. So what do we need? What do we actually use the sample spheres part of things for? Like, does anyone use this? Was this just for back when we were doing other things? Because I don't know, right? So, like, do we ever look up a light sampling sphere at all? Oops. Like, I don't think we do. So let's remove this, because that may be another source of confusion, is that we're generating these two things because we used to use one of them and we don't anymore. And just, like, getting that out of there will reduce the chances that we do something stupid, like are looking at one, like, because we're drawing one and, like, using the other, right? Which is really bad. That could be making us think like something positive, right? So this is why I say, like, you know, doing this pass to clean up the code is very important, because we've done all these experiments and now we need to condense down to just one so that we can focus on getting it right, and nice and shippable, right? Like, anyway. So, if we just take the sampling spheres out of here, who complains, right? Let's find out. So, I don't know what raise per probe is there, so if we get rid of this, what else we got? This, I don't know what that is. And this is just drawing it. So, like, if we turn off the drawing, is that it? So, yeah, so none of that was getting used. None of that is getting used. So that entire thing where we do, like, the interleave values, like, that whole thing just doesn't even matter. So this, like, we're only using this part of the entire thing. So presumably, if we went to this part here, So we've got this like light sample direction. Presumably, if we just deleted like the rest of this stuff, like this, it would be fine. Like, I think we just left this in here because we were using it, and now we don't. So let's just get rid of it and see what happens. Like, if I get rid of that entirely, does anyone complain? Okay. So basically, like, we know now that we're actually down to just the table that actually we care about, which is good. So that means we can also delete all this other stuff, right? So here is the only table, this is the only table we're actually using, is that. We don't care about any of these. They're not relevant, so they can all go away. And that means that the sample direction, like, bundle thing doesn't have to happen. So it's just the raw directions that we need. And if we look at the raw directions, not sure where these are actually defined. Probably somewhere. Sphere store. So where is sphere store? Okay. So the sphere store here, the raw directions is really the part we actually care about, and that's just the v3. The sphere store, I don't think we actually need. So if we look at spheres, in theory, that should just be like not even a thing anymore. It's not used in the output. Is it used in here? I don't think so. So yeah, I think like basically we can remove interleave directions. We can remove, I don't think cube store is used at all. So we can remove all of these, and I think we're good. Like, we can just remove all this stuff. Are we compiling this though? That shouldn't have compiled. So I think we're just not compiling HHsphere. So let's make sure we are. There we go. Okay, so if I remove this stuff, so we remove that, we remove the use of spheres everywhere. So we just have like generate some stuff for us and store the raw directions. No more spheres, right? No more sphere stuff happening. I think then we're good. So we don't need any of this. And now, like, our program is vastly simplified, right? And we're all good. So that's all fine. So now all we're doing is calling generate octahedral lighting pattern, and we have a thing that outputs that here, which I think is correct. I don't think we really need to modify it particularly much. The raw directions, though, need to actually be packed in a different way. So we want to, like, change the order of them. So that in here, like, we're gonna want to have this load properly so that you do the casts in like the right order, right? And that's easier said than done because it's kind of complicated to unwind in your mind. If you look at the way that it's working now, we have like this octahedron index and it loops over and you do 8 ray indices, right? You can see them happening here. And I don't think we actually want to do it that way. I think what we probably would rather do is build this one, do the loops the other way around, if that makes sense. So in other words, we walk the table in order. We do however many light sampling octahedron counts there are, we do that many in a row on the same accumulator. Then we move to the next texel, right? I think that's how we would do it. I think that's how we would do it. Yeah. Yeah. So if we're doing it that way, then we know that this output, right, is just going to be this table of light sample directions. The lighting octahedral map dimension is fine as a pound-defined output. We need to know that, right? The light sampling octahedron mask is not going to be a thing anymore because we don't step through them unpredictably. So that would go away. The light sample directions per octahedron, I don't think that would actually ever be used. So really all you need is the map dimension and the count of the rays coming out of a single texel. So it would be like, you know, lighting octahedral samples per texel, or rays per texel. Right? And that number is actually a parameter. We could generate like more or less of those depending on how much CPU power we want to spend versus the quality of the sampling, right? So instead of rays per octahedron, I think what we want here is rays per texel. And that would get printed. The octahedron count would not be a thing because that was sort of a surrogate. That was actually what rays per texel was, but I don't think we want that. And so then the total count, which is how many of these we're going to have, is just the dimension squared times the rays per texel. Right? So it's that. And since I don't know if square will evaluate fairly, I'll just do, or like a compile time, right? I'll just manually do it, like so. So that's the count, and that is just that's how many will be in here. And I think what we'd rather do, instead of putting this in there, we should make that be a automatic compiler-sized thing, and then we should just like assert. I don't know if we have a CT assert. We do. We should CT assert that like these come out correct because we want this number to always be the same as the number that we print out, and if they aren't, rather than forcing them to be, we would rather print out an error message. It's like, hey, by the way, this totally didn't work, right? So we probably want to do a thing that's like, hey, assert that the array count of the sample direction table is equal to the amount that we said we were going to do, and that way we rather than force it, we will, yeah, we'd make it do the thing. So raise per texel is here. So we have square the octahedron dim. I don't know if square. We should probably do it this way because, like I said, I don't know if it's that may be not for integers. It may only be for floats. I don't remember. Okay. So I think that's everything that we need to do to print out the correct thing, like, to the file, right? We then just need to think about how we actually want to sieve these properly, and you can see, like, we've got some kind of a, like, we put a bunch of directions out on this thing, and then we sieve them. right? Into like ones that go, I don't. It just doesn't seem like a very good way to do this. I mean, maybe it's the only way to do it. I don't know. But because so here's how we did this, right? So we allocate some space for this thing, for where we're putting. We allocate some space for like ray directions on a sphere. We randomly initialize them to white noise. So we start with white noise. Then we use basically like energy repulsion. Like we basically just like look and repulse points based on how many things are close to them. You know what I mean? And we stop when we are within like a range. Right? You can see here we try to get the distance to converge to some arbitrary thing we picked, right? And that's how we produced our sampling sphere. Like I said, the problem with that is that we don't guarantee we'll get enough actual points for any particular octahedron. So what I propose we do now is I propose we don't actually modify this algorithm at all. I propose we run this crappy one, go do a visualization of it. So, because remember, we were drawing the wrong thing. So we don't really want that, right? So go fix the drawing of this down in the sampling spheres drawing thingy. To actually draw them and colored by Texel, right? We do that, and then we should be able to visually see that the result is bad. And then we can pop back to H8 sphere and try to fix it. So if we have it all, if we've go ahead and do redo this loop where we loop through the texels, I guess like this. I don't even know that we care so much about these, but I'm gonna do it this way for now. So all right. So we loop through TY, and it's light sampling octahedron map dim. Lighting, sorry. Octahedron map dim. So if we loop over... I don't know why that's indented further. That doesn't seem to make a whole lot of sense, but okay. Why is that? Who is indenting? Is it this? Is there something like a hanging indent above here that's causing this to be busted? Apparently so. What's the problem, 4coder? Why are you confused? There must be like something if zeroed out up here that's like causing some weird, like everything is 1 over from where it should be. Why is that? Anyone want to guess? It's this, isn't it? Okay. Better? Okay. So if I loop over these txty values like so, I should be able to then, for each one of these, loop over the total number of rays per texel, and pick out like each one from the sample direction. These things come from a table that will have been loaded here. And we're really just going down these in order. So meaning we would start by saying like raydir equals the first one in the table. I guess we need to look at sampling direction. So so sampdir equals, you know, whatever the first thing in the table is. And then each time through here when we draw a ray, we want to go to the next one. The position of this thing looks like we're just kind of hacking it. So we can literally just say like, okay, the sample directions, I don't remember what the actual name for this is. It's ray D, I guess. So the ray direction we get out of here, then we draw this thing, and what I want to do is make the color of it just be something that only gets updated as we go through the texel area. So there'd be like a color index here, and you know what? The other thing we could do is just actually we don't even really need to use the debug colors. So what we could do is say like this is checker here. We could make just a checkerboard, right, where we do like either white or black. I don't know if we have the ability to turn lighting off easily for things. I don't remember how we did that, but it will make it kind of harder to see in that sense. But we could... Like, did these debug things... I don't remember how these debug things work. So, I don't know. We'll have to play with that later. But the checkerboard pattern would be like just the bottom bit. If the bottom bits of X and Y are different, then use one color, otherwise use another. You know what I mean? I feel like that's probably all we need. So, like, you know, you start out TX, TY, they're equal. If you step one in either direction, they're now not equal. You step one in the other one, and now they're equal again, right? So that should produce like a checkerboard pattern, which is all we need to see, I think. So I think that produces a drawing of the actual thing that we want. So now we just need to like run the actual program, have it print out the directions, and call it a day. Unfortunately, like I said, this program, I don't know that this is actually outputting in the correct order. I'm not sure. Yeah, so this loop is kind of busted. So we probably want to fix this loop. To look like this. Right? Like this wants to look like, I think, like this. So that we loop over the txty with the map dim. We don't really care about that. So this is the dimension, right? This is the octmap dim here. So we loop over the octmap dim, and then we've got raise per texel. And the total number of directions here is this octmap dim squared times the raise per texel. This is like hard-coded. So that to me suggests that like this should be Like, these are all, like, totally hard-coded, it looks like, for some reason. Which doesn't make a lot of sense. Maybe we'll do v2s, or do we have a u? Okay. Maybe we'll do v2u of octmapdim so that in here we basically say, like, look, the dimension of this thing, for the light atlas or whatever, is just going to be the octmapdim plus 2, which is what it should be. And then instead of having that dx dy there, we're just like, look, we loop through the x's, we loop through the y's, and we have arrays per texel, right? Okay. So you can even see how this is obviously wrong. Like, you can even see where the bug's coming from. So we compute the total direction count, like we were doing that before. We were computing it differently, but it still was like, how many of these do we want to put out, right? And then we're asking for a Poisson distribution that's the exact number. Now, a random distribution over the sphere is going to, on average, give you 1/8 of the rays on each texel. Well, not on each texel. 1/64 of the rays on each texel if it's 8 by 8, right? But the problem is, if you actually look at any given texel, it's going to be off by 1, like in either direction, because it's random. So there's going to be some that have like 1 less or 1 more on them. And so when you then go to output exactly 16 or something from that square, you're not going to get 16, right? That's not going to happen. You know what I'm saying? I'm hungry and I need some crunch. I feel like I need I need some little chicharrones. I feel like we need to take like a 10-second chicharron break. To try and get downstairs and get some chicharrones. But that's separate. That's neither here nor there, I suppose. All right, anyway. So yeah, this was kind of busted, and now it's a little less busted. So, but this is still a problem. So I feel like we would have to increase the total number of directions we ask for in the distribution. Like, this total direction count needs to be like higher, because when we pull stuff out of the thing, we gotta have more. There has to be proportionally more random points than we need. Otherwise, it's not going to come out to 16 per. It's just not going to happen, right? And so I don't know the best way to do that, but, you know, I also don't know how this thing knows how many directions there would be. That's a little bit weird as well. So I feel like this is just kind of a little broken, and I don't love it. This is fine in that you ask it to do some number of directions and it produces like a bundle, right? But I think we want something maybe like storage for this that takes with it the size. So like something like direction builder, or I don't know, direction gen, you know? So that you know how many of these you generated. I think you want that. You know what I'm saying? So generate Poisson samples here. Nobody calls. We call generate Poisson distribution. But nobody calls generate Poisson samples. So let's get rid of it. Focus on what we actually have. Nobody calls test func either. Okay. So when we call generate Poisson distribution here, maybe we give this like, hey, return us one of these direction gen things. And it looks like it doesn't care, like this displacements is just a thing that it uses like internally, it seems. So we don't have to return that. What is this used? Dir index equals false? What is that for? That doesn't seem to be a thing. Like that's not actually a thing. So it seems like this is bogus, I guess. I don't know. So anyway, if we take a look at this direction generate Poisson samples thing, if we imagine that this was going to return us a result here, the result directions, in fact, I guess we can just move it down here because I don't care. The result, I don't know why there's a printf, but I guess it's just because it prints out a status, right? It's like, it's printing out a status with a \r, so this just advances the line. Whatever. So directions equals directions, whatever, and result equals result, and blah, blah, blah. So if we want to in here take the total direction count that was requested and save it, now we can do that, and at least now we're passing around something that has a size, because we're going to need that eventually. So we've got that now, and that's good. And so when you do like a generate Poisson lighting pattern or whatever, I guess we don't care about this one because we don't use Poisson lighting pattern anymore, right? Yeah. So when we do generate octahedral lighting pattern, like we do here, somehow the octmapdim doesn't have a plus operator? Are you kidding me? Like v2u plus v2u isn't a thing? That can't be right. Can it be? Have we literally never had to add two of these together? Also, we do have a V... Oh, no, that's V3S. Never mind. I guess we don't. I mean, it ain't there. So I guess we just never needed that. We've only ever added operators that we actually use, and I guess we never used it. I ain't seeing it. So V2U just doesn't seem to have much in general. Like, there's hardly anything here for it. Is there even a V2U operations section? There isn't even a section for it. So I guess we want a thing here for V2 operations. Not a lot to see here, but probably something we want, right? Okay. Back to our story. So the Poisson distribution will now return like a thing that actually keeps how many there are, right? So this way we get input directions. We'll just call that input for now. So we generate Poisson distribution with the total direction count. And this is like the total direction count would be saved in here. You know what I'm saying? I feel like that's better. And we probably have sort of like a output dir count and an input dir count, and they're different because of that scaling difference that I said. Like, we know that we have to generate a denser covering if we want to be able to extract points from it. So the input direction count is going to kind of be like this times some extra. You know what I mean? Like, I don't really know how to sensibly figure that out, but it's going to have to be like, oh, you generate 20% extra or something, right? It's a 20% denser distribution or something, right? So it'd be like, hey, yeah, take the output count and, you know, we're going to multiply it by some scaling factor that we just randomly have to pick. And then we ask for that number, right? And the output direction count is actually going to be a different thing, right? I wonder if we direction array. Let's call this direction array. So that way, like, we can be a little bit better here, where we say, like, okay, we get an input direction array back from generating the samples, and we can allocate one of these. We could also have like a thing that allocates these for us so that we don't have to have all these mallocs around. Like, we could do this. Where we just say, hey, how many of those did you want, right? And we don't really have to care about this code at all because it's just some offline tool we run. It can be as crappy as you want, but I'm just trying to make it easy to read and simple, right? Because we have to debug it. So I don't want it to be, like, it can be somewhat horrible, but I don't want it to be, like, excruciatingly horrible, right? So, okay, we can allocate a direction array, and so now we can sort of do something more like this, where we say, okay, the result here gets allocated up at the front, where we say, okay, the result is alloctor array of the total count. We can also use this to get the other thing, which is like displacements. And we could also make these be E, right? Just simplify that a little bit. Like the elements of it. So it's just like a little bit cleaner. Not cleaner, simpler to read. So we allocate a direction array for each of these, the result and the displacements. Now that gets handled automatically. Then we just have to change this to, like, and in fact, we could even rename this directions. Then it's even simpler. So it's just directions.e is the direction itself. And then the displacements would the displacements will also be a .e. But otherwise, the code remains the same. Okay. So that's pretty easy. And then these for the outputs would do the exact same thing. So the direction array for the output would also say, hey, I need an alloctor array, like so, and off we go. So that's the basics of what we're doing. This here is not useful. This is. So raise per pixel goes on here. We've have it all. So we have our TX already set up and our array index also, but now we've got to actually write this internal bit to work properly. We also need to return the output here, so. And then we have to look at how this thing actually works. So all we're doing here is searching like in an n-squared slow way. This is just searching to find in the inputs, right? It's like we search over the inputs. By the way, I need to fix that. Like, you can't see the semicolon with the cursor the way it is in 4Coder right now. That cursor probably needs to be a little bit different. I'll have to remember to fix that. It's like too fat. You can't actually see what the thing is underneath it. Anyway, so input directions. Just called input, right? Yeah. So we're looking over the inputs to find one that is pointing in the direction we actually need it to. Assuming that we find it, we assign it to like a value that we know marks it as having been used, so we won't use it again. And then we output it as 1 for this thing. Right? We then probably want to make this really harsh. Like, we probably want to just, like, print an error if we don't find one. So basically, like, if, like, it'd be more like this. If we find one, great. If we don't, we're in trouble. So, like, if we don't find one, we, like, print out an error, like, that this is really bad. Like, for this texel, we could not find enough. Like, we ran out. Right? And we just want that to be an error because, like, basically, like, we need to go fix the code. Like, it's not good enough at that point. Right? And we need to fix it. Alright, so then we have our direction array that we get back from this. And the things that we're now reading are, we have the octahedron dimension, that's correct. And we have the raise per texel. Right? So this is really octahedron side. And so the V2U for the octahedron dim is going to be the side, like, twice, because we're only doing square right now, although we can change that, but at the moment we don't have any plans to. And the raise per texel is just directly in. I don't know why these are out of order, so you'd think you'd write it like that. Like, how many rays, how many things. Maybe you want it more like that. So let's do it this way. I don't know. Octahedron texel. There needs to be a better word for when you have a square texture, you're saying one of them. Something like that. I mean, it's really, really cumbersome, but oh well. And then here we have raise per texel. Right. So, and then the destination file, of course, which is a separate issue. So we get the octahedron side, we get the raised per texel, and we pass those in. And then later, when we do output sphere INL, we just pass the same things again. So actually, it's not hedron count. Sorry, it's octdim. So we'd pass the same thing. So I think that's okay. And then the output sphere thing just needs to change slightly, right, to be a little bit different. This is going to be one of them arrays, right? So this is a direction array. We output the sample direction thing. We output the mapdim, the raised per texel, and this is going to be like only one of them at the moment because we don't support rectangular output. Even though we would properly handle it, we just don't bother, I guess. We then have this thing here do exactly what you would think. The total direction account goes away because I now passed that through properly like I wanted to before. And off we go. Okay. So now I think we've got it all. We've have it all. And I think the whole process should now work, barring bugs, which there always are. But I think we're more or less good, right? Like, that should output the thing. And I don't think we'd need to do anything else. I mean, we have the kind of BS constant of 0.2. Or 1.2, I should say. But, you know, what can you do? So, if we've built it, we can now run the HH sphere program, and we can say that it's like 8, and that the raised per texel is 16, which I think is roughly what we were targeting. And then the destination INL is like, I don't remember, it's like sphere samples or HH lighting, or I don't even remember what the heck it's called. Handmade sampling spheres. Handmade sampling spheres. And so let's, like, kill this buffer. Let's run this program, and who knows what it's going to do. I certainly don't. And I think when this gets below 2.5, if it ever gets below 2.5, it might not. No, it did. So you can see here, like, it definitely has a problem. It can't find enough texels, right? Which may be due to bugs, I'm not sure. But anyway, that's the program running. We have to go make it work better than it does. But if we now look at those sampling spheres, what we should see is, because we're flooding the, if we didn't find one, then output 0, we can now much more easily see who was able to fill their quota, like, and who wasn't, right? Now, we also should be able to, like, our lighting will be totally borked because it's reading the table wrong now. Oh, what's this? This is good. This is saying that it's not enough. things, right? Oh, no, it's not. It's just saying that it's missing a parentheses before semicolon. Is that the total light? Did I print this out wrong, this number? Oh, yeah. Like, why is that word wrapping? I guess because this is an INL file. But anyway, you can see it's missing the closing paren. So, okay, so now we can change our stuff to read from this properly and draw it, but it's going to be wrong, so that's fine. Also, I don't know what this, it says there's a missing, a pound if that's hanging here, apparently. So I don't know what that's about, but. Did we accidentally? That all looks right. That looks right. I will say I don't quite understand what that if is for. So, you know what? This is what happened. We forgot to remove this when we commented this out, right? So that one, it shouldn't be there anymore. That was the only weirdness. Okay, so before we do anything else, let's go back to H8 Sphere and put in the missing closing paren, because the next time we run this program, it's going to output a bogus file if we don't do that. So then we can go through here and fix this stuff. So the ray weight here is now just always going to be, we know that it's the rays per texel, because that's always going to be the number that the ratio that we want to use, because we're always going to be summing over that many, right? When we loop through here, we now know also that this is not really ray index. So this is like, there's two things now. There's a ray index and a texel index. And right now, ray index is actually also texel index. So if you, at least I think, and that's wrong. So we don't want that. I also don't think we need to keep this around. Like, we're not going to be doing anything with that. So the transfer PPS pulling out of this ray index here, that is actually not correct, if that makes sense. So we need to do a slight modification here, which is to say that the transfer PPS value, there's really going to be a different way that this works. So the way that this will actually work is more like this. We will have on the outside where we're looping over the actual, like, the actual texels one at a time. And by the way, we need to make sure that this is actually looped this way. Yeah, it is. What we need to do here is say that actually transfer PPS is going to be summed by an accumulator. So whichever one we're on right now, we're going to have a transfer PPS accumulator, which is just one vector that we sum into over and over for each ray, and then the texel index that we are actually advancing across, that is going to pick out which transfer PPS value we're actually targeting. So these right here are going to be transfer PPS accum, like so. And you can see we already have a to-do here to fix this, because this is not really necessary to do it this way, right? We could make that better. So when we do that accumulation, we actually want to have both of those. And so now we've got two things. We've got the ray index as it moves through the table, and we have the texel index as it moves across, right? So this right here is texel index is less than this value, the octahedral map dim. So we're stepping across those. And while we're in here, we have this transfer PPS accum value, and that's going to be the thing that's actually 0. This doesn't have to get initialized because it will get written, each one of them will get written to, because we're going across this 8 here, right? like so. In fact, you could actually just say this is array count of transfer PPS, like that. So we're stepping across each one of the texels that we're gonna have to write. We're accumulating across all of the arrays that we're going to do, and that's going to be in here, and that's going to be over the raise per texel value, like so. And that raise per texel value, I can probably make this a little bit easier to read by doing that. The raise per texel value, we're just looping over these, picking out different directions to cast out of the same texel. And then when we sum it in at the end, like we sum it in right here. So we like accumulate on the same texel, write it out once to that texel. Then at the very end, we blend that into the texture map here. After we've done all 8, we load them up and blend them in one wide operation. Right. So now we just need to be able to step the table properly. And stepping the table properly just requires us being on the correct row. So when we look at this like direction offset, this whole nonsense, we don't really need any of this anymore. So really all we're doing is setting this once. There's like basically like a how should I put this? We'd be setting this once and it would just advance each time. So the walk table offset here, I would say probably all we really need to do is at the outset just set the sample dir to the correct thing here. Each time through, we just do the sample dir ray d and the sample dir walk table offset. We load those up, and then at the end, we just each time through the loop, we increment the sample direction. Probably, because there's so much float work going on in here, we probably can just spare the extra add, and then you don't have to do any kind of addressing. So it seems like that's probably the right thing to do, is to just step it. That'd be my guess. So at that point, we're left with we no longer have octahedral indexes. We just have like texel index and ray index, right? So for debug's sake, the debug pick value, it's really just txty and ray. So it would be texel index is the thing that equals debug pick tx. Oops. Like so. And ray index would be debug pick ray index. And again, like at this point, it becomes kind of weird that we don't just do the while loop in here as well, because there isn't really any reason not to do that. So you probably, like, this should probably be renamed. Instead of texel index, it should just be tx, because now it actually is tx. And eventually we should just make that loop over ty as well, one would assume. You know what I'm saying? So for sample directions, really this part just needs to be set to the correct place in the table. And in order to do that, we would need to know what row we were on. So this sy, right, is the thing that's telling us that. So it's, again, kind of annoying. It may make more sense, again, to just like push that in, like, to just start at the root of the sample table and just go through the whole thing by having the ty loop here. It's unclear why we wouldn't do that, so I might just do that. Because you can see here now there's just this extra nonsense for no reason, right? Like it's unclear why we don't just have it do the entire chunk at the same time. Like, why does this happen? We don't know. So it seems like we probably would want to just, like, take this loop and move it out. So grid raycast, rather than passing an SY, just passes the light probe P, the spec atlas. The spec texel A just would get computed directly in the thing. What about tile? The tile, I suppose, we would need to pass in now, right? So instead of spec texel A, you would just pass the tile, and then the rest of the stuff is exactly as it is. So this loop would come out in grid raycast, and we would take this part here and make this be the ty loop. Right? And the cast initiated part is really just a statistics gathering thing for us, so we know what this is. It's just going to be the total. Like, we do them all, so it's literally the entire table. It's literally total light sample direction count, right? So then we do the sample direction just starts at the beginning of the table. We walk the table, pulling out the correct tile each time, and that's our loop. So I think that's basically what we're looking at here. There's no such thing as SY anymore. It's just TY. And the tile is going to come in as up here instead of SY, right? We're not passing that anymore. And instead of spec texel, we're passing the tile. I don't remember what that is. It's some kind of tile thing. Or not. So what is that value? We just saw it. What is the name of the type? Light Atlas Texel. Oh, so it's just Light Atlas Texel tile, I guess. I don't know what that was for. We can put it back in if we need it someday. So yeah, this is TX. And the spec texel is now not A, it's just spec texel. The SY needs to go away. And this ray index needs to be clamped to I guess I don't know what Atlas index means here. Atlas index is just the global enumerator, I guess. So yeah, so basically, like, this is kind of just not necessary anymore. This can actually just be moved out. Like, we don't have to call this again, right? We can just call solution debug pick here, like so. Meaning if we're debugging, then this just happens. And I don't even know that we need to do that, because this stuff can now happen inside the old version. So, like, we can just pass down... We can just prep and pass down a thing that checks the atlas, and off we go, I think. So in grid raycast here, where we pass this debug pick, debug pick enabled would just be, we would just expand the check in, where did you go? Here you are. We would just expand the check here to check against the ty value as well. And so then we just do if the atlas index is equal up here. So this entire thing would just be like, we could keep basically exactly this. Get rid of the thing that calls it, grid raycast twice, and just pass true or false based, the solution debug pick. We just pass it if we happen to be the correct value. So debug ray pick, pick equals nothing. If we're equal, then it equals the debug pick, right? So that will pass down. So that leaves it off in the case where it's not the particular atlas, and on in the case where it is. The ray index has to be clamped now to whatever we called this value, so the per texel. And now I think we're good. So a lot of reorganization, but getting closer to a reasonable thing. Okay, so that should now... I guess we should, like, debug crashes, right? Because we're going to be, like, wrong. We're, like, stepping too far along something, or who knows what, right? So the first thing we want to do is, like, debug crashes in what we just did. Because, again, this is really, like, aggressively optimized code. So we've got a lot of, like, hand-tuned stuff that is going to have a lot of, like, fragility to it, right? Because this is, like, the most heavily optimized thing we have in the entire system by far. So that looks like a legit... That's not an unaligned... That's not unaligned. That's actually just off, which is good. It's easier. So it looks like we're stepping too much here. There's probably, like, one of the things on the interior is doing, like, a... is counting on something having been set up and walking through it only once. Although that's just looking up into the table. So that's like a problem with the walk table. Probably. let's take a quick look at walk table. Solution, light sampling, walk table, quadrant index. Starts in a reasonable place. Sample dir, walk table. Well, actually, just show me the whole thing. Oh, right. Yeah. So a 0, 0, 0 will make it so that it's, yeah, like, I mean, this should still not crash. It should be, we should make it so that this works fine. But when it gets to something that's 0, 0, 0, it will never step through the table. So I don't know what we want to do about that. Maybe just special case it in the walk table build. So like if we can. I'm trying to think of like how you would build these tables so that that would still work. So when we compute the walk table, right, you can see what would happen here is it never really would hit the padded max cost per array. You still would, I mean, shouldn't you march? I guess the problem would be maybe if T terminate is picked incorrectly, which it obviously is. And how is T terminate set in the case where it was going to be 0 like that? T terminate is 0. T terminate gets updated by T best. And so NV, the problem here is that NV ray D, right? NV ray D is wrong. So we probably just need to like actually do a safe divide here. Because if all of these are inf, because they're all 0, so nobody, like they will all be inf and nobody will be picked. It will be forced to pick a random one effectively. I mean, it's not random, it's predictable. It will pick, you know, the first one, I guess, right? But that will be inf. So we probably want to do something like comparing it and making sure that if T terminate is too high, if it's inf, you know, then it gets clamped. Something like that. Because my recollection is it needs to sample at the terminator. And so the problem is that if you never leave the square you're in, if you have no way of ever knowing where it should end up, then what's going to happen is that T terminate value is going to be inf in here. You can see when it ends, the probed sample P single is then going to be a completely out of bounds value. When we then do the sample, that's what's going to have this Texel pointer because the base offset that we compute, right, is going to be out in the middle of nowhere, and it's going to load a completely bogus value. So it's a very predictable error. The problem is, like, what do we set it to? It should never happen. So we only care about it while we're doing this debugging process of making sure the table doesn't have zeros in it, but we want to be able to run while that's doing that. So I think we just want to clamp it. Like, look, clamp this between, 0 and some large value, right? I don't know what, well, maybe we just want to do, like, if it's inf. Do we have an isinf? Like, some really large. This is terrible. It can be used, but if it's not, if it's a bogus value, we probably want to add an isinf for this very purpose, because we do have a case where that is what we need to know. What is this? What is this complaining about? Fatal error. Why can it not open Handmade Hero? Why are you not? Stop debugging. It cannot stop, apparently. Folks, debugging cannot be stopped. Why can't it be stopped? We do not know. Can we be billed now? Yes. What version of Remedy am I using? I may have to update. 3.5. Oh, yeah. I should probably update that at some point, because that's a bit out of date, right? Like, the actual current version is like 3.6.3, and I'm on 3.5. So we're in a, I'll have to remember to do that. We're like way out of date. Okay. So we need to fix that bug so that this doesn't happen on load, on like out of bounds loads, basically. And so we have to figure out like how we're gonna make that happen. So now we fixed the t terminate to be 0, which is good, I think. But we're still having like let's look at what so when we compute the diffuse atlas base offset here, I mean, no, like just not an acceptable value, in case anyone was wondering. How did this happen? If it's 0, how would we, does this also use an inverse? It may be that like there's no way to run zeros through this thing because it's, simply not built to have rays that don't march, right? Rays, they're expected to be normal, right? So yeah, I'm not sure why we're getting that, but unum broadcast 1 norm 1 over 1 norm for IUV. Yep, so this uses an inverse as well. So I think basically, like, I don't think there's any way to I don't think there's any way to shove zeros through this thing, unfortunately. Because everybody expects you to be able to undo the rate. The ray is supposed to be a normal. You know what I mean? So I guess we can't do that. So I guess if we want to do something like this, we have to output something that is at least a valid ray direction. And we can still make it be like 001, so it's very obvious that it's wrong. And of course, we also print out the values. So, but I guess we're going to have to just do cast straight up if you don't know where to go, right? Because we really can't, like, none of this code, it all assumes that because they're coming from a table, they all have to be valid, you know, normal. They can't be garbage, right? So let's try remaking our sampling spheres again. You know what? This is going to run really slowly because we're running it in debug. Although I did want to go get some snacks. So there is that. I wonder if that's like we should run it in debug mode so it's slow and then I run and get snacks. Okay. So in theory, if I build now, we should not have those, so we shouldn't get that particular bug. We may have a different bug, but we shouldn't get that one. Can I revert this buffer? No. So here we are, and you can see now that like our zeros have been replaced with ones in the Z column for like failed outputs, and we compile just fine. Now we can go see what happens when we actually run. All right, so actually that's better than I would have expected, so we're in good shape. I would like to know how to properly draw this thing. Like, why our debug lines are I don't know why our debug lines are like not lit properly. Like you can tell like this is sort of wrong. At least I think it is. Maybe I'm incorrect about that. But it looks like the fact that these are in the wrong place means they're not getting drawn in white and black as they should be. I'm not totally sure about that though. That could be incorrect. So let me take a look. So for example, when we draw diagrams, how does this stuff work? Is there anything that says what makes things emissive? I don't know. So it looks like enable lighting is actually still on for things like diagrams. So I don't know. It might be that there is no way to do that. Like I haven't really looked to see if that's something we really do. But so I'm not sure. But I'm gonna go into the lighting drawing thing and just see what happens if we don't move these up as high. Yeah, so it's just like lighting. Like they get lit, and even though I don't really want them to be, we don't have a super good way of avoiding that. So you can see the octahedral map pattern here, and unfortunately there's like too much other crap in the way. But you can see it, and you can also see like where the stuff is missing. Right, you can see the gaps. And those gaps are almost certainly the places where it, couldn't find values that fell within the texel because they happen to be like slightly on the wrong side, like towards one of the other tiers or something, right? Presumably that's what's happening, although we don't really know. But it's still a reasonable sampling sphere. It's not horrible at the moment. It's just not good. You know what I mean? Okay, so now we have to figure out what the heck is going on, of course. So there is that. So we're not out of the woods yet. But we're getting closer, slowly. Because we're obviously still not summing these things properly, but at least now we're not doing completely ridiculous stuff like we were before, where we were crashing because we were sampling out of bounds. So if we now look and see what's going on here, I guess we have some questions to ask ourselves about whether or not we're stepping through the texels properly and all that kind of good stuff. When we work on rows here, we create this accumulator, and basically we're going to be that ray, the weight that we add for each ray, right, is going to be based on the inverse of however many rays we cast for every texel. When we step through these, I feel like this should just work. Like, I don't feel like we should have to do anything special here. And after we sample, right, we're just summing the accumulator over the rays. That is a problem. So it's not a summation there. It's just setting it equal is all that's happening. So there we go. So now at least we're stably evaluating the lighting. We're evaluating it in the correct order. And we now just have to figure out like why we're getting. First of all, we have to fix the holes in the sampling sphere, which you can see here again. So we want to try and fix that so we're not sampling down all the time. And then we have two more problems. One is we're getting that light flooding, and we don't really know where that's coming from. But the other problem we have is also that when we move, there's some weird, like, on movement, we get some dimming artifact. I have no idea where that's coming from. Doesn't stand to reason that should be happening, so I think that's just a bug that is happening with how we're accumulating, or something. Something bad is happening there, right? Like it's being cleared or something, which is totally wrong. But we're pretty close, and if you look at sort of like, if you imagine you got rid of that dimming effect, this would be pretty stable, pretty good lighting, right? It's pretty close. It's not that far from what we actually want. So we have some weird things. We've got like the green bleed. We've got the weird dimming as we move. But we're pretty close to good, and we're very respectable frame rate wise. Even with all the debug stuff on, we're 30. We're well above 30. So I think we're probably able to do this at 60 FPS as well, right? I think we'll probably be able to button this down. And this is on an old machine too, right? Like, this is not on a new machine. Okay, so first questions first. How do we fix our sphere to not have this problem with being unable to find stuff? Do we just need to make it denser? Do we need to change the way we're doing this? Like, maybe this is just a bad way to do it, unfortunately. Are we picking wrong? I don't know. So, octahedral from unit vector. So this will be correctly using the +1 offsets. That all seems fine. And so I don't know, is like 20 like let's check by using a massively oversampled sphere. So this is twice as sampled, right? And I guess we might say this might not converge though, because this is an this value doesn't mean anything. It probably needs to be scaled like by the total direction count in some way. So like, you know, it would have to be increased or decreased correctly. So like this value probably needs to be lower at that point, right? This needs to be like something else, and I don't know. For a 2x, we should probably try to figure that out, what that should realistically be if we're going to use this repulsion. But, you know, that might also be an argument, like I said, for like we need to do something that's not repulsion. Like repulsion is just too sloppy. It's not looking good. Well, we'll leave it at that difference for now. That's just the difference between the maximum distance and the minimum distance. So it's the variance on the sphere. So, you know, in some sense, it's not entirely implausible that... Where did my command go? I don't know what happened there. It's not entirely implausible that you could continue to use it that way, but yeah. So 816 handmade sampling spheres. So we'll see if we massively oversample the sphere, will that like let it pick enough for each texel? If it doesn't, that suggests maybe we've got a bug where it's actually not picking properly, because with twice as many, you would think there would be plenty in any given section of the octahedron to get the number that was necessary, right? And this doesn't really look all that much different, right? So it kind of feels like it's just broken. Like, you know what I mean? And it's really weird that that would be the case. So I think like this may just be broken. Like this is not working properly or something. Because if the total direction count if the total direction count that you ask for is twice as many as you need, then how would you not, and they're like point repulsed, so they're relatively well distributed, how would you not get enough? Like, something is really off about that, but I don't know what it is. Is it because our get octahedral offset routine is busted or something? Like, you can see how this is working. It's stepping through the TX and TYs. And then it is, for every ray that it needs to output, it does raise per texel of those for that TX and TY by just looping through, like, literally n squared. Just looping through, looking for something that matches. And it just doesn't make any sense that you wouldn't have enough in it. Like, how would that be possible? I'm trying to think if there's an error in my reasoning, but it doesn't feel like you could possibly have so few on the sphere at that point that you couldn't sieve them. It just doesn't stand to reason. That seems like obviously has to be wrong. So that's what it did look like. And honestly, it really doesn't even look different. Despite asking for twice as many points. Is there something like that I'm missing here? Like, we call generate process on distribution with input dir count. So, like, what am I missing? I'm definitely missing something. I feel like we're going to need a snack for this. We definitely want to solve this problem, and we need a snack for this. So I'm going to call break time, and we're going to get a snack. And then we're going to check it again. We're going to figure it out. That's my official call. Everyone take snack break. Do it. I'll be back in a moment. All right. So we have two choices here, really. One is we just abandon this scheme a priori and say, look, we're going to generate them in a different way that doesn't involve picking. The other is we debug the picking because it must be broken. Unless somehow generating twice as many points in the sphere still somehow doesn't have enough on each octahedral point. Which doesn't seem to make sense to me. 16 was raised per textile. So we're generating 32 times 64. Yeah, we generate 32 choices per textile. And then when we go to look for 16 of them, we find that there supposedly aren't 16 in some of the textiles, right? Supposedly. That's what we are told. And if we look at the INL, you can see that it's like very specific. Like it's not like everybody is missing one or two. It's like there's very specific holes, like a giant hole in one of the things, and then another one is completely full. Which makes me think there's some kind of bug, either in the repulsion, so that it's like repelling things more at that point because of some way that we wrote it, or something else. I'm not sure. But we should probably try to debug the octahedral map thing a little bit, because I don't know, maybe that routine is kind of busted as well. Like, we don't know if that routine is right. It may be totally wrong. You know what I'm saying? Oh, and if you want to know the indexes, here's the indexes. Like 0, 0. Like, it's right on the edge, right? So 0s, 3s, 4s, 5s, 7s. The middle numbers, like 2, 2, that sort of thing, never shows up here. Right? So it seems like maybe the to me that it's possible that the thing that's doing the classifying is classifying wrong. Maybe. I don't know. There is one other possibility, which is that, look, an octahedron, by definition, warps a sphere. In the place where it is warped, it will be hard for that textile to find anything, right? Because it's covering less area of the sphere. You know what I mean? So, you know, I could believe it. Which is why also I'm wondering, like, okay, what's next? Chicharrones? Not enough. I should have gotten more. I need like 2 bowls of chicharrones. Is what I really need in life. The more bowls of chicharrones you have, the better your life is. I mean, I think that's just... Everyone knows that. We don't need to belabor the point. Okay, so... I guess what I would say here is I do think we may have to change the way this is working. So I might not bother debugging this part because when I think about the fact that the octahedral map is by definition a warp of the sphere, then to me that suggests that I am going to have, like, I'm not going to get a choice. I'm going to have to distribute points in the actual texels and make them be evenly distributed like in texel space, because otherwise you can't evenly distribute things in sphere space, or like you're like that's not going to work because the octahedron doesn't pull evenly from those. So it kind of does feel like I need to do something slightly different here. And I don't know exactly what that thing should be, but maybe what that should be is we try to do more blue noise on like inside the texel, but as far as like texel to texel, we don't try to evenly distribute those across the sphere because like it wouldn't help if we did. Or we try to do something else where we just like seed things. Okay, here's the thought. What if we here's my proposal. You ready for this? Hold on to your monkas. What if we seed the number of rays per texel that we want using white noise inside each texel? So we start with something that is white noise with 16 rays coming out of each texel face on the sphere. We then run the distributor, but we refuse to let any texel leave the octant that it is in. What do you think? Anyone? Anyone want to weigh in on that? So we start with 64 by 6, 64 8 by 8, so 64 texels. Octahedron. We generate white noise shooting out of those texels. We then run the sphere repulsion, but we don't let any rays leave the texels that they are in. So there's always exactly 16 per texel, but they can repulse to try and get themselves spread more evenly apart. Right? Won't you get clamping on the edges? Well, I mean, yeah. You can't move past the edge, but the point is other texels should, in theory, other samples that are in the neighboring texels should, in theory, push you still, right? Now, the fact that it's a warped space, is a problem, but I think we should go do something like that, though, because we can start by just doing 16 rays randomly generated white noise out each texel, and that's someplace to start anyway. And then the repulsion just has to try and improve that slightly, right? Like we could just use the white noise directly, but it's not the best sampling pattern because it's going to be a little clumpy. So we could just look at it that way. So maybe let's start with that. Because we can start by using the white noise directly without actually having any repulsion, and then we can turn on the repulsion and work on that separately. So let's suppose we basically nerf the repulsion part, right? And we're just going to seed the directions out of the texel. So we use the like octahedral to offset something thingy, right? So this unit vector from octahedral will give us a sampling so the oxy coefficient is going to be like 1 over the value rate. So as long as we put these into UV space, basically, unit vector from octahedral should give us everything we want, right? Yeah. So I think that would do it, because that's a 0 to 1 value, right? So let's see what happens. Let's see what happens. I'm going to call unit vector from octahedral. So inside HH sphere, what we're actually going to do is not this. We're going to seed these differently, right? So in this place points on the sphere poorly thing, we're going to change this to place points on the sphere 16 randomly per, or not 16, rays per texel randomly per texel. So when we call this, we would no longer be able to tell it how many we wanted. We would have to specifically say, like, what's the octdim and how many rays per texel we have. We would then have yet another of the exact same structure of loop. Like, everything basically just looks like this in these routines, right? So we basically just go through and we say, all right, the total direction count is now, as it was before, it's always going to be octdim x times octdim y times rays per texel. And then we're going to seed them by doing this nonsense. And maybe I'll call this seed dir index just so it's not confused with any variables below that we might use. We're going to call unit vector from octahedral, and we need to basically have this direction that comes back. When we do generate octahedral lighting pattern, this now no longer has to happen. So the things that come back from generate Poisson distribution are just going to be correct. There's no actual work that needs to be done. So this pick would go away, and you would just call generate Poisson distribution, right? So in here, we just say generate Poisson distribution, and it would just give you back the actual answer, right? So what we do need to do here, though, is generate random unilaterals that would give us the correct offset. So basically, like, the V2, this is like the UV coordinate, right? We would generate white noise by, generating a unit vector from a portion inside the texel, the texture that represents one texel, the specific TY/TX texel here. So we would essentially do, like, there's going to be like a U like a U span, like how big is a or like text dim basically, or like a UV dim. I don't know how you want to say that. I'm not sure what a good name is for it. But it would be a UV dim times a unilateral. So we're going to go like some distance, like, you know, some random distance along the UV dimension. Like so, and the UV dim is like the octmap dim 1 over the octmap dim, right? So it would be like TX plus some random unilateral. So we start at like whichever texel we're on, we add some fractional value to it, and we multiply that by whatever the UV reciprocal is, or like, you know, I don't know, inv oct dim, something like that. That seems about right. Does that seem reasonable? So we would have a inv octdim, which is like 1 over the octdim. And that way, like, it steps through correctly, and yeah, is that it? Oops. And then we just like write those out in order. So is there really no inverse operator there? I guess there isn't. That's fine. And so maybe that's right. We don't know. So let's try HH sphere. We disabled the rest of it, right? Yeah. So maybe that's right. We don't really know. But we can look at what it made and see how bad it is, right? So, you know, they at least look semi-coherent, so it's not entirely fictional what's been written here, but, you know, we have no way of knowing if it's really correct. Right. So let's take a look. If we now recompile, we'll be compiling with those new values. We can at least look at them in on the drawing, like, and see what we have. Okay, so something weird is happening. We're only getting one, like, we're not actually moving all the way around. Did I mess up my for loop there? Oh, are these UVs actually, is it not actually UV? Is it actually positive, negative? Okay, so actually it's -1 to 1. Right? So that's why we're not getting, yeah. So it's actually -1 to 1. These are, so the division of that, well, so does that mean it's like -4, like -1 is the 0th texel and 1, yeah, I don't really know. So I guess that's fine. That's pretty easy to fix if that actually is all it is. It would just be, you know, 2 times the value, and then you bias it back by 1, right? So that's not really a problem if that's all it was. I'm not sure, though, because it's been a while since we worked with these octahedral maps, so I don't really remember. Oops. I have to actually run this again. All right. So there's our sphere, right? And, you know, it's kind of sucky. Like, it's clumpy, exactly as you'd expect. But it's a sphere. And, you know, and it's a sphere. I don't know what else to say. The copying artifact thing is still definitely there, so we should, like, totally unrelated to it, it seems. That's just, like, stable. And the green bleed is there. So those are separate bugs, presumably. I think we're getting closer. So let's try now to, like, if we did want some repulsion here, I'm trying to think of, like, how we would actually do this. So if we were doing some repulsion, I'm assuming what we would mostly do is just say if the displacement would take you, would change your texel index, then you can't do it. Probably. Something like that. I don't actually know. Look, I'm not sure how plausible that is as an actual algorithm, right? I might try it, just because why not? So effectively what that would look like is when you have one of these, so we're calling unit vector from octahedral, we would just call octahedral from unit vector and then clamp, right? Or quantize. We could also just call get octahedral offset, which already does that quantize. So maybe we just do that. So in here we say, all right, we turn the repulsion back on. We go into the update step, which is this, I think. And where we would update the direction, which is here, we only update the direction if it would stay in the same quadrant, right? So we basically say, like, if the octahedral, if they're not, or if they are equal, we can take the step, otherwise we can't. So if get octahedral offset for the direction that it was and the new direction are not the same, and the octdim coefficient is whatever the light atlas would have said that it was. So I think that would just require us doing this. It has the padding around the border, right? Which is kind of annoying, but that's just how computers have to work, I'm afraid. So the atlas has the octdim coefficient in it, and so we can, in theory, just make it so that you can't push it in a way that would upset that particular apple cart, right? Um, and I think that's all we need there. So, we have these for other things, but not this particular one. So I think that would work, although it's, you know, I don't really know. That's kind of clumsy. I don't know that we have any reason to believe that such a particular repulsion thing like this would actually work in this regard. This criteria probably won't be correct either. So it's a bit dicey, but, you know. And you can see, like, it quickly locks up not being able to really displace anybody, it looks like. So I'm not sure where to end this. It looks like the difference here is quite substantial, right? Like it's like that's how far it got, which is not far. So again, and the problem is, since the thing is warped, you can't really compare. I guess you could compare distances in UV space, but like, probably not good. So I don't know. Not sure how useful this really would be. Like, again, it's like not horrible, but it's definitely not like good. So like it might make more sense to try and do this like on the UV map and let the sphere be warped as a result. I mean, it's not as good because you're trying to sample in the sphere space, but I don't know. I'm not really sure what else to do. This isn't my area of expertise, so I don't really have a lot to draw on here. Like, sampling is not my strong suit, so I don't really have much to say um, about like how that should be structured, right? Um, But either way, like, let's say that that's good enough for now and look at some of the other bugs, because really this is probably not our problem at the moment. Like, the fact that this sphere is not great is not what's causing our more severe artifacts. So we can probably afford to start looking at those now, since we know that the tables are at least not completely messed up at this point. Um, if that makes sense. So, you know, we've got like our ray cast now that we had from before here. And these should now be more sane. And you know, the ray casts themselves look fine, right? I mean, it looks like it's actually correct, and like, I don't see, you know, I mean, I just don't see a lot of evidence of bugginess going on there. That should be -1, and it's not. That's going to bug me, so I'm going to fix it, even though it doesn't really matter. So yeah, so I guess like our next question is like, where are we getting this weird green blur from? That's probably the hardest one to solve, unfortunately, because it's going to be very weird to try and determine what the heck that's coming from, I suppose. But the only other one we really have now is that dimming that happens when you move. So the light leakage here seems like probably the most important thing to look at. Because, like, where is that coming from? I guess one question I have is, are we doing more adding than we should be able to? Are we adding more frequently than we should be able to? And that I don't actually know. It's just a linear blend, though, so that's not true. So I don't think we're at risk of doing too much addition because we sum by the inverse. Like, the ray weight here is correct in that it prevents you from summing up more than what you started with, right? So that seems fine. And the transfer PPS values are blended, right? They're 1 minus. They're lerped together, so you're not adding any energy there. So I don't know how we're getting this sort of... I don't know how we're getting this energy bleed. I'm curious, like, it's definitely just like a very clear energy bleed. Like, it's like you can see it happen, right? Like, in fact, like, I don't know if I can turn off the scaling there. The light map debug buffer. So let's take a look at what we're putting in there, because I think the light map debug buffer basically gets like some garbage values put in it. Yeah, you can see here for like filtering out, like looking at particular textures. So we could definitely change these values to something else to look at. I mean, it seems like we probably just want to do this. So if we want to take the UV min and the UV max and just set these equal to like 0 and 1, would that just show us the whole map? Yeah. Maybe I'll look at slightly less of it just to see. Oops. Wait, shouldn't that have... That should have done... I guess it's really that tiny. I guess... Why that looked counterintuitive to me. What I just saw, but I guess I'm wrong. Like, it looks like the stretching, like, in... I don't get it. Oh, is that because we currently stack in Z only? Yeah, okay, that's probably because these are stacked oddly. Which is probably also something we would want to fix eventually. Now that I think about it. Because they're only stacked too high. Which don't make a whole lot of sense. You know? Stacking them too high is kind of dumb. Like, they probably should be, you know, X by Y. And then just 2 copies of that, you know, for the Z or whatever. So that's probably a mistake. But, oh well. You know, we're probably not going to fix it, right? So, it does look like a pretty consistent light bleed, where it's just you're getting energy added to the system and it just spreads throughout the system. And the question is, where is that energy getting, where is that energy coming from? You know? Like, it's coming from somewhere, but I don't know where. And, like, there's very specific places where it's unstable. Is it because it's sampling from an apron in some way that it's not supposed to happen? Like is something weird happening there? Like, it's very clearly, like, only possible when certain areas are available. Which is odd. And the fact that the copies are wrong as well it's so weird. Like, it's very strange what's happening. Like, that I can't even come up with an explanation. It's one of those times we have them every so often on Hammer here. I can't even come up with an explanation of what's going on there. Like, if you ask me to write this exact thing, what I would have to do to make this happen doesn't seem commensurate with what I would expect. Now, I want to go look at the copy. Because it's obviously wrong. Let's start there. I'm going to kill this buffer of values. The copy obviously doesn't work because we're getting that weird, like, on every time the voxel slides, the values are all wrong. So the part where we actually copy the voxel is just totally busted. So this block copy atlas thing is totally bogus and doesn't work. Why that would be, I don't know. Because in theory, we shouldn't really have changed much, but I guess it's because of how we are computing, like, the offsets of these things, because we did sort of change how they were sized. You know, we obviously screwed that up. So I'll start with first things first here and just say, like, Z doesn't matter anymore. So we should be able to assert that the dvoxel Z value is always 0. And if it's not, that could be one of our problems, right? Like, if the dvoxel z value is wrong, then that would explain a lot. So maybe that's the problem. But I don't know. Doesn't look like it. So dvoxel z is correctly staying at 0, which is what we would expect. So then the question is, are our other dvoxel values somehow wrong? So the way we're doing this is we're taking the origin value and we're looking at the delta between them. We are then trying to move. So every time the origin moves by some number of chunks, we assume that the number of chunks is aligned with our voxel cell dimension evenly. Which could be completely wrong, A. But B, even if it was completely wrong, I'm not sure I know why we would see the behavior we're seeing. I guess we would see that behavior if it moved too much. So if the invox cell dim caused the multiple to be too high, that would do it, I guess. So I kind of want to know what these values are. Like, so in normal operation at 60 FPS, these should always be like 1 or less, right? And so I'm kind of wondering maybe if they are if they're not. Looks like we don't have an abs for ints. Fine. So I'm just kind of interested to know, I guess the problem is I have to kind of enable this later because on the first time through, it's not going to be the case because you're moving to, you know, a different one, but... some kind of garbage like this. So, you know, the first time through, fine, get it set up, but the next, from then on, we should never see any sliding, right? It should always be like one tile at a time. All right, so it's correctly only moving a single tile at a time. Right? And yet somehow we're getting this weird difference. Why are there 2 copies of block copy atlas? Oh, it's just a, yeah. So, I mean, that all looks pretty sane. Like, I don't really see what the problem would be there. So it could be something we'll have to look at this more carefully. I'm going to turn off those overlays because I don't really need them at the immediate moment. I might also be interested in a very slowed down version just to see what's happening. I mean, it's unmistakable. On the copy, everything gets dimmer for just a brief flash. So the copy is just wrong. But I do not know how it's wrong. Here's another question for you. Suppose we were to turn off interpolation, what would it look like? So if the t-update blend were just 1, so there's no interpolation anymore, we just see the whatever happens on this frame is what we see. Right? Which is this. That is just really weird. So I do think we're probably going to have to construct some test cases here. I don't think there's any chance of us debugging this in situ, right? What we can debug, we have, I think. So I think we're going to have to create more test cases. And you can see, like, so whenever this thing moves, you know that it has changed the placement of the lighting. You can see very clearly that it blinks once for every move. It is clearly on the copy. So the copy is just wrong. But we have no idea why the copy would be wrong. It doesn't make sense for the copy to be wrong. What is validate Texla Atlas? Interesting. Hey, so what if we turned this on? Wonder if we get any traps. We don't. We should, though, eventually, as we, like, right? That's just saying that we don't have super high values, I guess. Or not super low values, it looks like. So it does eventually trap. It just takes a little while. But that feedback eventually hits. So you get out of bounds values like right away. And it's from the raycast because it can't be from the copy since the copy validates on either end. Right. So you get like out of bounds light values right away. And again, we really don't have any idea why that would be. I'm guessing we should probably call it a day for today because this is going to be really involved, right? We're going to need at least another 4 hours just of setup time to like track this down. Because we definitely have problems with the Light Atlas now that have something to do with how we, simplified it down. And we're gonna have to go through the whole like re-approval process, like to like narrow it down, right? And again, that's just how it is. Whenever you try to do extremely like optimized code like this, where you're pushing everything into like these extremely like special case ways of doing stuff, your bugs are very hard to track. Right? There's really no way around that. It's why we don't normally write this code if we don't have to, right? Like, modern languages don't make it easy to write optimized code. So it's kind of what you would expect because there's probably some rather obvious stupidity lurking in here, but it's just very hard to see because we have turned the crank so many times on it to get it down to something that will run fast enough that we don't really, we don't have the luxury of a simple walkthrough, right? Adding some opt-in bounds checking in here would probably be a good idea, right? Like validating that probe p single is in bounds would be good. Like we can add some assertions here that are relatively unobtrusive. They'll get compiled out when we turn off asserts. So we could put some things in here that would probably be okay. That would help us know that we're not doing something weird like that. For example, that bleed could happen from things like fetching out of bounds or something like that. It could happen. So let's take a quick look. So probe p single. Didn't I just look at it? Probe sample p single. We could do some assertions here. And just verify that this is okay. So basically we'd say, okay, pull out the base location, like so, and assert that it's not like out of bounds of the thing that we're looking up in, which is the diffuse atlas. So like assert that this is in bounds of, well, does the atlas do that for us? So it would be nice if this had a way of just telling you if you were inside or not. But it doesn't actually seem to. So you can see here that we actually have the thing that we want, which is this test, but we don't have a way to access it outside. So we could do that, right? We could do like a vector is inside or whatever. So we could do something like voxel index is in dimension. And put this in there so that the checks for each one being inside would be something you could call elsewhere. So then we would just do voxel index is in dim of the light atlas. We'd assert that as probably like this would be an index. So if we just pass the xyz to the function here as our assert, then people outside can also call that assert, which is what we want, right? So here we would just say assert that voxel index is in dim, and there's diffuse atlas and a place that we're trying to check. And that would, in theory, tell us. Although I guess probe sample p single still has to be converted. So we still need something that maps into there, which I guess we don't really have. Right? Okay. So we would need to actually divide by the by the cell dim, I guess. So I guess we actually kind of did have what we needed, because although, you know, although we probably do want this function as a separate thing, I guess we actually can just use the grid. So we'd say get index for p and then assert in bounds. Right? Something like this. So when we're debugging, at least this would tell us if we ever tried to fetch out of bounds. And I don't know if we quite did that correctly, but, you know, maybe. So let's let this trip a few times in a in a debug build, and let's see if we can see if there's anything particularly squinky going on there. Okay, so there's the actual sample point we're trying to take. That is obviously wrong. It's not only wrong, but it's weird. So you can kind of see, like, basically these all have the exact same pattern. They are all, like, totally bogus Z values. There are some X's that are off one apron-wise, but the Z values are just complete garbage, right? So I don't know if that's because I'm doing something wrong here, but that seems bad. So what would make us happy here? So the total bounds, let's look at this SP, right? So the total bounds, like, how is that Z value? How are we getting that Z value at all? Okay, yeah, I get it. I get it. I totally get it. I totally get it. Here's what's happening. Okay. So in compute walk table, we don't anymore bother to check Z values because there is no Z voxel anymore, right? We only have an XY sort of the things. That's all we have, right? So when we step through the spatial partition, and I don't remember if we're drawing this or not. I guess I'd have to turn that off. But this is very good. Like, so this answers a big part of our question of why we're messed up, right? So this is very good. This was a very important. I'm really glad we just added this. This was big. This will help us tremendously. Okay. So what's happening here? If we've have it all, we gotta update our remedy. We need to be able to kill our app, which we can't anymore. It looks like that stopped working. But we let me put this in O2 and simultaneously let me go and draw the actual cells again so that we can see them, which, we don't need this right now. Spatial grid. That's what I want. Draw spatial grid. So debug draw spatial grid will step over each of the grid areas, and it will draw the bounds of them, right? If I do that, this will just draw just the boundary box. So this shows what grid cells there are in this spatial grid, right? So I gotta turn off all the validation that we were just using so that I can actually look at it. Okay. So here are all of the grid cells, right? And you can see that it's just a two-dimensional array of grid cells. And so what we're doing with the marching table is the marching table that we use to find out where we are. If you're normally casting inside the actual geometry, it's totally fine because you'll always hit something as you're trying to go up or down, right? But the geometry is incomplete, and like in some places, like there's like we don't have anything there, a ray would just go and it will go forever, right? Now before that wasn't a problem because we actually had an apron for stopping like we do right now, where there's an apron along the outside where if you hit that apron, you stop marching. But we don't have that for Z anymore. So what happens is you just go as far as you go in Z, which can be infinitely far, doesn't matter, right? And then you try to sample, and you sample complete garbage out there. So whenever we do that sampling, we're going to have to clamp, right? We're going to have to say, like, if you've left the area, if you've left the bounds, then you stop. And you wouldn't sample that ray, right? You wouldn't download a Ferrari, and you wouldn't sample that ray. That's almost certainly where our bleed is coming from. We're sampling completely out into garbage land, and then that contaminates everyone. That also explains why you only get to bleed sometimes, because if you move to a place in the world where all of the lighting computations are being done in places that actually will hit something, then you will not get the bleed, right? So I think that totally explains this problem. The question is just, what do we do about it? I also don't know why we were getting like -1 in X. That seems broken. So that may be like a legit rounding bug or something that we have in the walk table, or like it's hitting the apron wrong. Right? So I'm not sure what we want to do about this. One thing we could do about this is we actually just, when we sample, we clamp the sample to the cage. So we just clamp it to a valid value. That has the bonus of working for everything that would be outside, so that might be the best way. The other option would be that we discard. So if you are outside, you just don't sum that one in. It's just 0. In theory, this should never happen in properly constructed environments. So I think we should just do whichever one's more efficient, because we won't have to care about the quality of the result in those circumstances, because they're only there for catching bugs and like numerical errors and stuff. It's not actually there to do any kind of like real work that we care about. So it probably is just whichever is more expedient, like throwing it out or clamping. Probably clamping is easier, because that way it doesn't introduce any kind of branch. It just kind of says, all right, the indexes will at least now always be valid. It's just you may end up fetching something that you probably shouldn't have bothered adding or something, right? That's my guess. So yeah. So here where we end up with a probe piece single, and then you can see here what we're doing is we're producing here with inv-seldom and total bounds. This floor function here is what's doing it. So yeah, so you can see us actually, we are clamping right here to... Okay, so we already are doing this clamping. So I guess I spoke too soon. This won't actually solve our bug, because we are actually doing the clamp, it looks like. But that doesn't quite add up now, does it? Because if that were true, then why... why when we ran this before were we able to sample out of bounds for arrays that were equal to 0? Is that just because the clamp wouldn't work on like inf or something? Like something still seems a little bit fishy there. Yeah, I would have assumed that inf would just be fine in that comparison, right? I mean, I'm always a little hazy on what SIMD will do. But you know, inf and negative inf should just compare as would a large number in that direction. So you would think that clamp would correctly clamp it down. So that should always be clamping, so how the heck did that ever actually sample outside of where it was supposed to sample? Like, that doesn't make a lot of sense. That just does not make a heck of a lot of sense. Like, we should be able to set that value to whatever we want. Right? So I wonder if there's like a subtle bug in here somewhere where there's some way we can actually sample outside. So yeah, I don't really know what's up with that. I don't know what to make of that. I'm pretty confused. So you can see like the general flow of this code. We start by producing the coordinate by flooring this is basically the voxel lookup. So P, right, is the place we're going to sample. We subtract the minimum value, which is exactly what you would expect. We then multiply by the inverse cell dimension, which is the same as dividing by the cell dimension. We then floor that. That gives us our voxel coordinate. Our UVW is where the fractional part of that, which is what you would expect, right? We then say, okay, the maximum place that you could sample on this voxel, the maximum address you could use is the dimension of the voxel minus 111, right? Like it just subtracts 1 from that. We clamp between 0 and that maximum value the base chord and the base chord plus 1. So those are the two corners like of the voxel that we'd like to sample, right? We take the difference between them, which is our way of saying if we flattened up against an edge, we don't want to step in those directions at all, right? And then we produce the base xy by saying, okay, whatever the minimum is that we're going to sample, we multiply that by the stride. And then we also add here, like, whatever this nonsense is, which is basically like the row stride for z, I guess. Tile row stride. Times txy. Okay, so that's the offset for the specific like the actual texel. Right? It's the xy offset of the texel. And then you just sample that thing, which is exactly right. Yeah, so I don't see how that was screwing up exactly. I wonder if we kind of need to go look at that code again. Maybe to provoke that crash that we had with the zeros in there, to see what was actually happening. So I kind of want to do that. So I think I'm going to do that before we call it a day here. So in our walk table, like, I'm pretty sure all we have to do is just load this up and spam a 0 in here. I'm pretty sure that just makes us crash, right? Yeah. So if I look at those values, I just want to get like a good understanding of exactly why that particular piece of code is crashing. I could have understood other pieces of code crashing maybe, but now that I've looked at this, if it's all clamped, how is that happening, right? So here, let's examine these actual values so we can see what they are. So we're going to take an F chord here, right? And it's just all garbage, which is what you would expect, right? Well, you know what? Those are actual nans, though. So that might not clamp. In fact, it won't. You would have to actually nan check that. So that would explain it, if that's actually what's happening. So that actually looks fine, though. Like, I would have thought that nans wouldn't clamp, but they did. Like I said, I'm always a little hazy on what SIMD will or won't do there. So these all actually look correct. The min and max are both zeros, and the delta is 0. So it does. It does actually clamp nans. So that's great. So the question is, why did base offset end up being so busted? Which is the actual value that's offensive? So base XYZ is min XYZ times stride XYZ, which is right. And min XYZ is zeros. I don't follow. So if base offset is computed from base XYZ, right? Then we know that it's wrong because base XY, the reason this is messed up is because base XYZ is garbage values. Base XYZ is min XYZ times stride XYZ. That should just be zeros, right? Plus this line here, which should just be correct, is TXY. So TXY is broken. So it's TXY that's actually the problem. Okay. So actually, I misinterpreted what was happening before. Really, it's just the fact that it can't invert that value is producing a bogus TXY fetch. So when I thought this has something to do with the actual grid cell, it doesn't. That's a lie, because that always gets clamped. So it's just the TXY that was actually causing it, and that comes from R, which we do know would be wrong. So I guess, like, surprise, it turns out this wasn't actually a problem. Oh well. That's a little bit of a bummer, but what can you do? Because that would have been nice if it turned out that, if that had actually been happening, then that would have probably been an easy fix, but no such luck. Okay. So let's take the bogus value out and put it back to where it was. All right. Well, I guess we got to call it for today, and we're going to have to pick this back up next time, when our goal will be to look at these last two problems here and probably have to dig in pretty hard. I don't know where they're coming from. I don't have any guesses at the moment. So we're kind of just going to have to go through slowly but surely and eliminate sources of problems. It's too bad because we're really close to good. It's too bad about this because it's very close to being a really good lighting, actually. But we're obviously just sampling really weirdly. We have a weird thing, too, where the light, you can see as it goes through, because we have this weird problem that's a separate problem of the lights as they go through other lights themselves are occluders in the system right now, and we don't handle that properly. So you get this weird thing too that's a separate issue. That's what's happened when you've moved through things. Separately, I would also ask what the heck that is. Oh, that's the light. Yeah, so in this case, you can see like this, our light is actually moving through another light, right? It's this light here. We can actually probably see it if we change the drawing area. Why is that only drawing sometimes? Doesn't that seem bad? What's up with that? So you see how Y seems like it mostly correctly works, although it doesn't work right there. Oh, that's just because it's inside something. That's why. Never mind. Yeah, I mean, we have some really weird problems, right? And I think we're close, but it's going to be a real grind to get down to 0, right? We're close, but it's going to be a grind. Unreal Engine 6. All right, I'm going to call it for today. We're going to have to look pretty carefully at this stuff. That's going to be a real grind next weekend, unfortunately, but that's just where we're at. So we will do it. So I'll be back here next weekend to take a look at that. Until then, everyone, have fun programming, and I will see everybody on the internet. Take it easy, everybody.